You can fix anything. Episode 1, Kitchen Scales. In today's world, a lot of things are made as cheaply as possible to maximise profit. If a company can save $10 on 10,000 units, they saved $100,000. The cheaper an item is, the less repairable it is. Bringing the price down has another effect. Besides less repairability, paying a technician to repair something may cost more than a new one. A good example is these kitchen scales. The mechanical ones might be a good idea if they're built to last, but if you want accuracy, you'll need digital scales. The big problem is that when something goes wrong, there is usually nothing you can do to fix them. Case in point, the heart of this circuit board is a blob of resin. You might have seen this blob yourself, or at least in bigclive.com videos. Under the blob is an unpackaged and unknown IC. This circuit board belongs to some kitchen scales which I accidentally destroyed while cleaning them. You may remember these scales from such videos as Can you refill a butane cartridge with LPG or propane part 1. There is no way to repair this. I checked the components and the problem is under that blob of resin. But with a 3D printer and modern electronics, we can repair, rebuild or repurpose anything. I can fix this so it will be repairable in future. Not only that, I can make it better. Follow along. It isn't just about these scales. You can learn how to repair any scales or even make your own. First up, the microcontroller, an Arduino Nano. The Arduino Nano is a small, complete and breadboard-friendly board based on the Atmega 328P. It's a smaller version of the Arduino Uno. It can be powered via USB or other power supply of 6 to 20 volts DC. You can buy these on eBay for about $9 Australian. 16x2 LCD with I2C interface. Besides being broken, one major downer to the design is the display and buttons are on the top where you usually place a mixing bowl, so a redesign is in order. That gives me free rein on the size of the LCD I can use, as well as plenty of room for the internals. I went for a 16x2 character LCD with a nice yellow backlight. I purchased 2 of them for $13. They come with a separate I2C interface board. You can drive it directly from the Arduino. That would require soldering 9 wires rather than 4, so for simplicity's sake I'll just solder on the I2C board. It can go on 2 ways, underneath to keep things slimline or on the back of the LCD. That's how I'm doing it. I'll hot melt glue it on first. Yes, these have the dreaded blobs too, but in this case it's a good trade-off to keep the component price down. Now some solder. Now it's just voltage, ground and 2 data wires to the Arduino. This is the non-I2C code. It uses the liquid crystal library. We aren't going to use that, so let's find some code. You don't have to be a genius to do this kind of thing. Google is your friend. Just keep looking until you find a code example that works. This one from robotique.tech looks like it will do the job. It uses the liquid crystal I2C library. I had to download it from GitHub. Paste in our code. With that done, we can connect the Arduino Nano and upload the code. load cell and HX711 analog to digital module. Apart from the plastic shell, the load cell was the only other reusable component. Like the LCD, it may be possible to connect it directly to the Arduino, but again, for simplicity's sake, I'm going to use the AD module. Here it's about $5.50 or $7.60 for it and the load cell. I already purchased this for another project, so I'll use the AD converter with the original load cell. I can experiment with the remaining load cell later. The HX711, like the I2C module, has a ground, a power and 2 data lines. We just need to connect the load cell wires in the right order. I'll solder on these header pins. And finally we connect it to the Arduino. I soldered the LCD and AD converter power wires together. Let's plug that in and we'll head back to the Arduino IDE. In this part of the video, originally I'd used Rob Tillart's HX711 library. But later I lost my code and for some reason I wasn't able to get it running again. For the final code linked in the description, I used the HX711 ADC library instead. Next we'll go to examples, and right down the bottom of the screen is HX711 and I'm choosing kitchen scale. Let's compile and upload that. Open up Serial Monitor and select 115,200 baud. A quick montage where I copy and paste the scale code into the I2C LCD one we had before. A few edits. And some calibration. And it seems to be working backwards. Not thinking for a second it may have been an easy fix in the code, and rather than change the wiring, I'll just turn the load cell over the other way. That did the trick. Some basic calibration with something of a known weight. Incidentally, a good way to calibrate a scale is with something like an iPhone. Providing it hasn't had any repairs or modifications, it should still weigh what it did when new. 3D printed front panel assembly. I designed a front panel assembly and frame in Tinkercad and printed it on my Anycubic Mega S. It took a few attempts to get right, mostly due to inexperience. It came out warped at first. Bed leveling and printing it with a brim made all the difference. Assembling it is straightforward. Carefully tighten the LCD screws without breaking it. The mechanical force required for this power switch is slightly too heavy for this application. Perhaps a push button style switch would be better suited for light devices. Center frame assembly. I printed it in a neat silver filament, basically because it's all I had. Fortunately, this one came out right first try. The support material was collapsing, so I gave it a little help with hot melt glue. Probably should have changed the settings to supports anywhere. I kept the original base and designed everything else around that. Checking fitment of all the pieces. I'm reusing the top, not the prettiest thing with the unused buttons and LCD window, but I can 3D print another one if I want. Time to glue it together. I used hot melt glue and then super glue for extra strength. Component assembly. Probably not the smartest idea to use hot melt glue to stick down the charging module, but we'll worry about that if it comes loose. I made a mistake here, initially thinking I'd need 3.3 volts when the LCD requires 5. That's an adjustable step-down converter. Fortunately, I found this handy USB charger. I just removed the USB port. That will give me the 5 volts I need. The push button is dual purpose. Short presses cycle through grams, ounces and pounds. A long press zeroes the scale simply by resetting the Arduino. I thought the LED on the power switch was a nice touch. Note the welcome screen. This is an older version of the code. I'll demonstrate the unit and reset functions at the end. I like the white pearl, but it's too transparent, so I printed another front in matching silver. Now the final assembly. Please note links to the components I used as well as the block diagram and code are in the description. If you have any tips or questions, be sure to leave them in the comments. This is the block diagram of how I wired all the modules together. The only difference is I ran a 5 volt wire to the LED on the switch I am using. Finally, the code. First we have the included libraries, physical pin assignments, variables, LCD initialization, load cell initialization and calibration. We set the push button switch state. Held down is the counter for how long the push button is pressed. I'm using a software reset because I don't know how to zero the scale. Write in the comments if you can help with that one. The main loop reads the scale, sets the cursor location to 0,0, reads the button. If it's held down, it increases the timer. When the button is released, anything under 6 will increase the unit mode. Anything above 6 will initiate the reset, which zeros your mixing bowl or whatever. The rest just prints the unit name and value. Ounces and pounds are simply multiplied from grams. Here you could add your own units. Think tablespoons, cups of flour or cups of sugar. Anything is possible with code, you just have to imagine it and make it happen. It ends with a delay of 50. Just demonstrating changing units with short presses and a long press for 0. I calibrated it with 2 different model iPhones. The accuracy sits within a gram or 2 of both. And there we have it, kitchen scales like no other. Fully working, programmable, upgradable and repairable. Because I have the code, I'm free to change anything about how it operates. If you enjoyed this video and want to see more repairs or builds like this, be sure to like and subscribe. It really helps my channel grow. Thanks for watching.